Alrighty, today we're going to be learning about different chemical reactions and being able to classify them into different groups. And so our objective for today simply is to be able to look at a chemical reaction and then decide what type of reaction is this. And this is going to help us so when we're looking at actual products of a chemical reaction, we'll be able to figure out what they are a little bit easier once we know what type of reaction we're looking at. So most basic chemical reactions can be classified into 5 different categories, and we're going to go over each one of these. So the first two kind of go together, single replacement and double replacement. The next two, even though it doesn't look like it, actually go together as well. One is called synthesis, one is called decomposition, and then our last one, combustion, is the one that you may have heard of before. Obviously, when you combust something, another word we use for that is burning things. So let's start with our very first one, a single replacement reaction. In a single replacement reaction, a single free element, that's the key there, is knowing that we're talking about an element that's by itself reacts with a compound. So again, in this case, typically you've got, usually that's an ionic compound. So you've got a metal plus a nonmetal. And what that single element does is it replaces one of the elements in that compound. So this element that's over here is going to replace either that metal or that nonmetal, depending on what the element is. So for example, here is our free element, and again, this is just an example. There's no real element A or X. But as you can see, what happens is that let's say A is a metal and B is a metal. Then A, notice what happens. The A basically kicks the B out. So now the B is by itself, and now the A is with this, whatever this nonmetal is. If A were a nonmetal, so A is a nonmetal, then this here, this would be your nonmetal, and the nonmetal would basically kick out the nonmetal. So the X over here would be by itself, and the A would be with the B. So depending on what this element is, it will either kick out the metal if it's a metal or kick out the nonmetal if it's also a nonmetal. Okay, so some examples. So zinc, the metal, and here we've got an acid. Hydrogen is the positive one, sulfate is the negative one, and so the zinc is going to kick out the hydrogen. And so what we see in our product side here is that now the hydrogen is by itself. Notice it's a diatomic molecule. There's 2 of them. But now the zinc is with the sulfate. So in general, when you see a reaction where one element is by itself and then it basically boots out one of the other elements and then it's together over here on the product side, that is a single replacement reaction. Okay, here's another one. You've got copper reacting with silver nitrate. Metal, metal. Here are the nonmetals. So the copper is going to kick out that metal. So now the silver is by itself, and now the copper is with the nitrate instead of the silver. Okay, and then our last one here, here's one with a nonmetal. So chlorine is a nonmetal, and so is bromine. So notice that on this one, the chlorine doesn't kick out the sodium like it has been up here. On these two, it's been kicking out the first element. On this one, it's actually kicking out the second one because that's a nonmetal. So now we've got the bromine by itself, and again, also a diatomic molecule. And now the chlorine is now with the sodium. So notice on this one too, we also had to balance the equation. Because this bromine, when it got kicked out, it made 2 of them. Because it's diatomic, we had to put that 2 there to balance the equation. So now we've got a balanced equation for all 3 of them. So single replacement reactions. One element is by itself. It replaces an element in a compound on the product side. Now, a double replacement reaction is actually really similar to a single replacement. The biggest difference is that basically with a single replacement reaction, you start out with that single free element. But in double replacement reactions, they're just occurring between 2 ionic compounds. So in this case, you're not starting with one element by itself, you're starting with two compounds. So basically two of them, the metal and the nonmetal, is reacting with another metal with its nonmetal. So in this case, notice again, we don't have an element by itself. But basically here, A and B represent the metals, and then X and Y represent the non-metals. So notice that all that's happening in this reaction is the A and the B are switching places. So now if we look at an example with real ones, we can see in this case, again, different from a single replacement because there's no element by itself. But when we're determining these reactions, we can't just look at our reactant side. We also have to look at our product side too to make sure that silver and that sodium, did they trade places? When we come over here, we can see that now that the silver is actually with the chlorine now, and the sodium is now with the nitrate. And so yes, that is a double replacement reaction. Okay, on this one, notice what happens here. We've got sodium and we've got hydrogen. Those are our two positive ions. And then we've got hydroxide and chlorine. So again, the two positives are going to switch places. So the Na goes with the Cl, and now notice here that the H goes with the OH, and you might be tempted to write HOH, which is actually fine, but as we know, the more common way of writing HOH is actually just water, H2O. And then in our final one, we've got NH4, which is our positive, chlorine is our negative, and then again, we've got the metal positive, the hydroxide negative. So again, our positives are just going to trade places. So the NH4 goes with the OH, there it is right there, and the sodium goes with the chlorine right there. And in this case, probably just by convenience, I wrote them. There's actually nothing that you need to balance here. All three of the equations are already balanced. So single and double replacement reactions. Single replacement, you start with one element by itself. With double replacement, you don't, but in both cases, things are just switching places from one thing to another. Now a synthesis reaction, kind of switching gears here a little bit. In a synthesis reaction, two or more substances combine to produce a single, more complex substance. So the key here is understanding that you start with two things that are separate and you end up with them somehow together. So for example, hydrogen gas, separate from oxygen gas, you light a match, they ignite, and you get water. So in a synthesis reaction, basically you're making something. The term synthesize means that you're making something. So in this case, we're making something from 2 or 3 or 4 other things, and you always end up with one thing at the end. So in this case, we've got calcium hydroxide reacting with water, and that's making, calcium oxide, and we're making calcium hydroxide. So again, two things coming together to make one. It's being synthesized. And then here, carbon monoxide reacting with oxygen gas to make carbon dioxide. Okay, again, pretty easy to see. You always end up with one thing when you start with two or more things on the reactant side. Okay, now when I said single and double replacement went together, that kind of makes sense. Synthesis and decomposition go together because they're basically opposites of each other. Synthesis is you're making something. In a decomposition reaction, you're starting with a single substance and it's broken down into two or more other substances. So in this case, we're starting here and we're ending with two or more things. So it's basically the opposite of a synthesis reaction. So a couple of examples of that is basically that same reaction from before. If you run electricity through water, the water will break down and it will form hydrogen gas and oxygen gas. It's pretty much same thing here. Mercury 2 oxide will break down into just plain old mercury and oxygen. And in this case, sodium chloride breaks down and you get sodium metal and chlorine gas. Notice on these there was some balancing that we had to do, and that's part of writing a chemical equation. So we've got single and double replacement, we've got synthesis and decomposition. Now you might ask, how are these things broken down? Usually a couple of things will do it. A lot of times if you run electricity through them, if you heat them, those are the kind of things that will break compounds down. Basically, we got to break the bonds that are between these atoms. Okay, and then our final one is a combustion reaction. And a combustion reaction occurs when a hydrocarbon, we'll talk about that, reacts with oxygen, and it pretty much always makes carbon dioxide and water unless it's missing something from there. A hydrocarbon is a compound that has some type of ratio of carbon and hydrogen. Those are question marks since you can't read them. But it's any compound that has carbon and hydrogen in it. So like propane, C3H8 is a hydrocarbon. Methane gas, CH4, is a hydrocarbon. Okay, it's a compound that just has carbon and hydrogen in it. Okay, so in these reactions, again, the hydrocarbon is just some combination of carbon and hydrogen. It reacts with oxygen. That's the combust part, is when it's burning. It's reacting with oxygen. And you're making carbon dioxide and water. Okay, so some examples. Here's the example I just gave you with methane. Okay, methane is CH4. It reacts with oxygen. This is a principal gas that's found in natural gas. So if you have natural gas at your house, this is the reaction that's happening that's creating the heat for your stove or for your furnace or whatever. Okay, here's the propane reaction. So this is natural gas. This is like a barbecue. Your barbecue is filled with propane. If you're using a gas barbecue, it's probably a propane tank that you have. And again, pretty similar looking, reacts with oxygen, makes CO2 and H2O. Just takes a little bit more work to balance it, but same sort of idea. And then our last one, this one is called hexane. And in hexane, you can see some pretty big numbers here. I think this is one where you have an odd-even problem, so you have to double everything. That's why the numbers get to be so big. But these ones are pretty easy to identify because it's always reacting with oxygen, always making CO2 and H2O. Okay, so we're going to look at these reactions, and then we're going to be able to state what type of reaction is occurring. Okay, so first of all, let's balance it. 1 barium, 1 barium. 2 chlorines, 1 chlorine. So let's stick a 2 right there. And then 2 potassiums. 2 potassiums. And then sulfate, sulfate. So all we need to do is put a 2 right there. Now hopefully we recognize this reaction as the barium and the potassium trading places. And that is a double replacement reaction. Okay, in our second one, we've got water, 2 hydrogens, 1 oxygen, 2 oxygens. So we're going to put a 2 right there. And then we're going to put a 2 right there to fix the hydrogens. Now we're starting with one thing. It's breaking down into 2. So this was a DR, double replacement. This is just a decomposition reaction. Okay, in our third one, we've got a single element by itself. It's replacing another element. It kicked that copper out. So that is a SR, a single replacement reaction. And I believe to balance it, we've just got those 2 coppers there. So we're going to put a 2 right there in front of the copper. Number 4, we've got H3PO4, SrOH2. So here we can see it looks like the strontium is coming over with the phosphate, and then the H is going with the OH to make our H2O. So to balance that, let's see, it looks like 3 hydrogens plus 2 makes 5, so that's a little bit off. Let's work on something else. Like for example, I see 3 strontiums here, so I'm going to put a 3 right there. I see 2 phosphates over here, so I got to have 2 phosphates, and that probably is going to help us with our hydrogen problem, because now we have 2 times 3 is 6, and then again, be careful here, 2 hydrogens, but then times 3 is another 6. So we have 12 hydrogens all total. So over here, I'm going to put a 6. And I'll bet that fixes any oxygen problems that we have. The PO4 we already took care of, so I'm not worried about these oxygens right here, only these oxygens right there. So 3 times 2, again, 3, 2, 6 oxygens. And now we have 6 oxygens. So it's balanced. And again, we can see that the hydrogens and the sulfate or the strontium are switching places. That is also a double replacement reaction. Okay, number 5, SO2 plus H2O makes H2SO3. It's already balanced, and 2 things are coming together to form 1. So that is a synthesis reaction. And number 6, we've got a hydrocarbon reacting with oxygen, making carbon dioxide and water. That is a combustion reaction. And then to balance it, this is the one that was a little bit tricky from before. 6 carbons, 14 hydrogens, put a 7 there, 14 hydrogens. But now we're going to have 6 times 2, 12 oxygens, plus 7 oxygens makes 19 oxygens all total. Well, we can't have 19 because we're going to have an even number here. So this is where we're going to have to go back and double everything. So change that 1 to a 2. The 6 is going to become a 12. The 7 becomes a 14. Now we have 24 oxygens here, plus 14 more oxygens makes 38 oxygens. So that means we need a 19 right there. So we end up with 19 O2s. Okay, let's see, we're kind of getting a little cluttered here. Let's take a look here. We've got sodium and copper. The sodium and the copper are going to trade places. Now the copper is with the nitrate, and then the sodium is by itself. We've got 2 of those nitrates, so we're going to go ahead and put a 2 right there. And now we have 2 sodium, so we're going to put a 2 right there. This element was by itself at the beginning, so that is a single replacement reaction. Okay, and then number 8, we're starting with one thing. It's all together. It's going to break apart into 2 things. So that is a decomposition reaction. And we've got 3 hydrogens, and here we have 2 hydrogens. So to make them the same, we're going to put a 2 in front of the H3N. That makes 6 hydrogens. And then we'll put a 3 right here, and that makes 6 hydrogens on the other side. And then that 2 also goes to the nitrogen. And hey, what do you know? There's already 2 nitrogens over on that side. Okay, and then one more here. This is, as you can see, hopefully you see it's another combustion reaction. Pretty similar to number 6 up here. This one's kind of like that one, but let's see. It's going to require a little bit of work. 14 carbons, 30 hydrogens, 15 there. And again, that's where we're going to have that odd problem is there with the with that oxygen, because 14 times 2 is 28. So we've got 28 oxygens plus the 15 oxygens equals 43 oxygens. But again, over here, we can't have that. So we're going to have to double everything. 2, that 14 is a 28. The 15 becomes a 30. And then we're actually going to end up with 56. We're going to end up with 86 oxygens. So yes, that number right there has to be a 43. Which you're thinking, oh, that's a really big number. Well, yeah, but we don't have any other choice. So that actually is the correct answer, and then it obviously is a combustion reaction. All right, let's head to our next assignment.